Thanks, Luke. Thanks, John. Yes, great to be back here. So a little step away from lung mechanics to the basic physiology of lung gas exchange, one of my favourite topics which I share with our co-conveners today very, very happily. So we're going to be helped by William of Occam, who said that plurality must never be posited without necessity. To paraphrase that, perhaps just keep it simple, which is what we're going to try and do, and what can be a very complex topic. So we're talking again about ventilation, diffusion, mismatch in the lung and its effect on gas exchange, in particular in understanding the behaviour of the gases that we use, our anaesthetic gases in everyday practice. Bit of a revision of what we spoke about last year, where we suggested that the concept of dead space was a lot more complicated than we wanted to believe or have been taught. And the reason why this is important is because VQ scatter and its consequences are basically universal in all our anaesthetised patients. And we see this in just things we measure on an everyday basis in those alveolar, arterial, AA partial pressure differences, where we typically see numbers like this with an end-tidal CO2 in the low 30s and an arterial CO2 in the high 40s in our ventilated anaesthetised patients. Very, very common numbers, you'll agree. What you don't see on an everyday basis is that the same thing's happening with your anaesthetic gases as well. So these are typical numbers we've measured in patients anaesthetised with sevoflurane with significant end-tidal to arterial partial pressure differences throughout the course of your anaesthetic. And this is a key part of the partial pressure cascade that is present in every patient throughout the course of your anaesthetic. That cascade of partial pressures from the inspired, through the end-tidal, the arterial, and then the mixed venous partial pressure. So this is the bit in the middle, and it's a substantial contributor to that partial pressure cascade, which of course reverses in direction at the end of the anaesthetic when you turn off the inspired gas. That cascade tips it up the other way as the gases are gradually eliminated from the body. So our understanding of the drivers of these AA gradients and VQ mismatch is the Riley model, which we spoke about last time, concepts generated many, many years ago. Looks like this in West's textbook, with the ideal compartment in the middle, dead space and shunt on either side of it. And it gives us those familiar mixing equations, including the Bohr equation, which measures dead space for us. And if we're measuring the alveolar dead space, the Bohr equation looks like that. We went through this last time. And the AA gradient, the end-tidal to arterial partial pressure difference, is reflected in the difference between the numerator and the denominator of the Bohr equation. You're all very, very familiar with these concepts. However, we showed that in patients who are under general anaesthesia, in this case two groups of cardiac surgery patients studied by Jan Andre and myself in different studies, we showed that whereas we'll measure typically a Bohr dead space of between 20 and 25%, typically in this population, in fact in our study the mean Bohr dead space was 23%, measured using CO2 partial pressures. At the same time, using the same sample of blood and the same expired breath, the dead space for our anaesthetic gases was 50 or 60%, not 23%. And in fact, this is closely related to the solubility of the gas in the blood. And we went on to try and explore why this should be, but basically it reveals how the Riley model really can't help us in understanding any of this stuff. So just to recap, the Riley model tells you that if we measure the dead space with CO2 in the usual fashion, using the Bohr equation, it tells us the distribution of ventilation between the ideal compartment in the middle and the dead space compartment on the right looks like this. But no, if we use sevoflurane, it looks like this at the same time, which is just bonkers, really. Makes no sense at all. So unfortunately, Riley is a failed model in many respects, because real lungs look like this. They are distributions of ventilation and blood flow. Where the blood flow gravitates towards the left, towards the low VQ compartments, and the alveolar ventilation to the right. And because VQ ratios are fractions, it's always best to look at these things using logarithmic scales. So this is a log scale on the x-axis with VQ ratio 1 in the middle, 100 on the right and 1 over 100 on the left. So that's why they call these log normal distributions, because on a log scale they have this nice Gaussian distribution. And you can measure the degree of mismatch and scatter from the log standard deviation of those Gaussian distributions. So your lungs hopefully look like the one on the left, with tightly matched narrow distributions, but your anaesthetised patients will look like the one on the right, with a log standard deviation of typically between 1.25 to 1.5, with significant VQ mismatch. And the whole concept of that old-fashioned term of waste of ventilation comes very clear when you look at distributions like this. You can see how all that alveolar ventilation on the right there is really not engaging with blood flow, so it is indeed waste of ventilation, and it's the contributor to alveolar dead space. What you can also do when you model these sorts of distributions is you can actually work out the distribution of gas exchange that accompanies these distributions of ventilation and blood flow. And here we've got the distribution of oxygen uptake on the left and of CO2 elimination on the right. And you can see how they're completely divergent. So the notion that there's some ideal compartment somewhere in the lung where all the gas exchange is occurring is just false, and it always has been false. At least in patients with significant VQ mismatch. It's true of patients with no VQ mismatch, but that's not what we're interested in. Now you can also work out the distribution of your anaesthetic gas. So here's your allophane, your isoflurane, your sevoflurane, and your desflurane. You can see how as the solubility of the gas declines, as the more modern gases have a lower solubility, the distribution of their uptake moves to the left, towards the lower VQ lung compartments. It's a basic fundamental feature of the relationship between solubility and gas exchange, is that less solubility means lower VQ, maximum efficiency of lower VQ ratios, maximum efficiency of gas uptake and elimination. So all of a sudden all this makes sense, because for our CO2, which is highly soluble in blood, we can say we've got maybe roughly this much waste of ventilation, this much dead space, because the distribution is to the right. But for our anaesthetic gases, SIBO and DES, where the distribution of uptake is much more to the left, there's much more waste of ventilation. And that's why we measure these vastly different dead space values. And in fact, the modelling these multi-compartment distributions does a very good job of predicting this behaviour that we measured, this relationship of solubility to dead space for all the gases, on the basis of these mechanisms I've just showed you. All right, so the problem is, this perhaps all looks a bit complicated. You know, these are 25, 50, 100 compartment lung models. Oh gosh, this all looks pretty hard work. How am I supposed to sort of make that work if I'm interested in this topic? Well, I'm going to put you that there's a very simple alternative. All we need is 2 compartments. Importantly, there's gas exchange occurring in both those compartments. One of them has low VQ and one has high VQ. Pretty simple. For simplicity, I'm going to put to you that the easiest way to organise this is to say that the VQ ratio in one compartment is the inverse, the reciprocal, of the VQ ratio in the other compartment. That keeps it as simple as possible, still. And I hope that William of Occam will be happy with me doing this. So we can then go on and say, okay, what's the gas exchange that we compute from these distributions going to look like? Well, they'll look like this. You'll have this much oxygen uptake and CO2 elimination happening in the low VQ lung compartment on the left, and that much in the high VQ lung compartment on the right. As you can see, CO2 and the oxygen are exchanging in very different parts of the lung, but we already know that. Nothing new there. All right, so what we want is to work out just what these different VQ ratios should be. What we want it to do is to equal the gas exchange that we would compute from a much more complex log normal distribution, but more importantly, we want it to equal what we've measured in our patients. We want it to give us a mean alveolar dead space of 23% for using CO2, our core equation of CO2. It turns out the magic number is 5. So in the low VQ lung compartment, we have a VQ ratio of 1 to 5, 1/5, and on the high VQ lung compartment, it's 5 to 1. If we do that, we get values that closely approximate what we see in our anaesthetised patients and what we measured in our studies. Okay, but what about the anaesthetic gases? So we can compute the gas exchange in those two compartments again for our three agents, ISO, SIVO and desflurane. And it looks like this. Once again, we want it to agree with what we've computed from our sophisticated log normal distributions, but more importantly, we want it to agree with what we've measured in our patients in our study. And in fact, and we want it to give us these alpha dead space values. So how does this simple model perform? The answer is really well. So what we measured was a dead space of a bit over 50%, and what the two compartment model gives us is something very, very close to that. And that's on the basis of this 5 to 1 split in VQ ratios. In actual fact, it's a little bit more complex than this, so if William of Occam will forgive me for a moment, this works really well and optimally if we actually have a small, true shunt lung compartment as well as the two main gas exchanging lung compartments. So a true shunt lung compartment where there's no gas exchange occurring gives us the best fit for all the gases, CO2, oxygen, and all anaesthetic agents. But it's still a pretty simple model. The Riley model is absolutely hopeless. The Riley model will tell us that the expected dead space would be about 30%, when we know it's actually 50 to 60. The multi-compartment model is pretty good. It's just under 50% estimate for dead space for the gases, for our free anaesthetic gases. So, we have a simple model. Why does it work so well? Why does it give us such a good approximation of what we're measuring in our anaesthetised patients? The answer is pretty simple, actually, it turns out. Because when you compare it with the log normal model, which we know works really well and gives us good predictions of the dead space for the gases, this is why the magic number of 5 turns out to be so important. Because those two VQ ratios that we've nominated for those two compartments, they sit at these 2 points in those distributions. The peak of the blood flow and the peak of alveolar ventilation lie more or less at those 2 points. So what those two lung compartments are doing is they're capturing the centrality of the low VQ gas exchange that's occurring in the lungs and the centrality of the high VQ gas exchange that's occurring in the lungs, and packaging it into 2 compartments and generating outputs which closely approximate what the more complex model does. So in summary, there's no definitive alveolar dead space. It varies enormously with the solubility of the gas in blood, and the Riley model has never been able to do this. The reason is because Riley told us the Riley model said that you could talk about a lung compartment in the middle, a lung compartment where all the gas exchange occurs. That's just not true. For that reason, Riley's a failed model in terms of understanding our lung gases in anaesthesia. Realistic distributions of V and Q do a very good job of understanding the behaviour of our gases because they allow us to generate these distributions of gas exchange. But it turns out that the simple 2-compartment model of reciprocal VQ ratios does an equally good job. Importantly, there's gas exchange occurring in both those 2 compartments. That's why it works. And it does it for all the gases, respiratory gases and all the anaesthetic gases. So, the good news is that you can try this at home yourself. This isn't terribly esoteric. You can actually apply this to your own work if you're interested in this topic. So the Brigham simulator, which Chris has developed, has getting a bit of press now, very deservedly, and Chris has kindly humoured me by adapting the Brigham simulator to incorporate this concept. So in fact there's a version of this which is now /Peyton at the bottom there, which has 2 alveolar compartments, and you can actually nominate the distribution of VQ ratios between those 2 lung compartments on the right there. So I've got it set to 0.2 to give us that 1 to 5 and 5 to 1 ratio in the 2 lung compartments. What this does is it generates realistic AA gradings for the uptake of sevoflurane in this example. And what that does, of course, is it will then generate a realistic simulation of the partial pressure cascade that we expect to see in our patients, and which we've actually measured in previous studies. So it's doing a good job of simulating the reality of the physiology of our anaesthetic gases in real life. And on that basis, I will thank Sir William of Occam and you for your attention. Thank you.